Okay, so in this problem, as you well know, because this is a homework problem, the author asks you to find the displacement at C and the slope at B. Now we're doing conjugate beam, so the first thing we have to do is draw the shear force and bending moment diagram. I won't take a little shortcut because I know you guys can do that, but if you look at the problem, you can see that with the symmetry of the loads and the geometry, I'm going to know that my reactions are 4 kilonewtons on each point. And then I'm going to quickly draw the shear moment diagram. I won't go into as much detail as we have in the past, because again, by this point in the course, I'm hoping that you can draw the shear force and bending moment diagram. So if I start off with my shear diagram with units of kilonewtons, you can see that the shear force is going to be what? Well, a force acting down like that is going to create negative shear, so we're going to start out at minus 4. There's no load, so it'll stay constant. And then the reaction of minus 4 will bring it back up to 0. Again, no load, so no change. Then I get a positive shear at the reaction, which matches the end shear. So you get something that looks like this. So you got two zones of constant shear on the end, and in the middle, really no shear. So that if I do the moment diagram, and this will have units of kilonewton meters, then what do we have? Well, we have a change in our change in moment is this shear, which is negative 12. So I'll go down to negative 12. No shear, so the shear will stay the same. And then a positive shear, so the change in moment will be the area of that curve. 4 times 3 gives you positive 12 and brings you back. So this will have a value of negative 12. That look familiar? I hope so. So then you go to the conjugate beam. And let's see what that looks like. So let's first draw the conjugate beam. So we go back to how our supports in the real structure map to the supports in the conjugate beam. So a free end in the real structure is what in the conjugate beam? You guys can play along. Fixed in. And then an internal support becomes a hinge. I think I gave that one away. So hinge, and then the other free end becomes fixed. So there's our conjugate beam. And now we're going to apply to that the moment diagram as load. So this is negative moment everywhere, so that means it becomes a negative load, and negative load is down. So it'll have the same shape. In fact, if you wanted to, you could just transfer the moment diagram the way it looks right to the conjugate beam. And just remember that the load is down. And now that load will be 12 over EI. Now what does the problem ask? The problem asks for the displacement at C. So the displacement in the real beam is the moment in the conjugate beam. So this is still point C. Here's B, and here's A. So I got to find the moment at this reaction. So let's draw the free body diagram for that, just kind of conceptually. So I'm going to break it apart at the hinge, right? So there it is. So I'm going to have now a moment at C, a shear at C, and a shear at B. No moment at B because it's a hinge. And then, of course, applied to that, I'll have whatever this load will be. So if I want to find the moment at C, I can sum moments at C. I have the force, but I don't know what the shear at B is yet. So let's find the shear at B first. So the shear at B I can find by looking at the middle section from A to B. So the shear at B will be here. And then of course I also need the shear at A. Again, there's no moments because there are hinges at each side. And then applied to that will be the load. So if I sum moments at B, I can find the shear, A. One of them is A, not B. This is A, sorry. So if I sum moments at A, I can find the shear at B, pass that on to here, sum moments at C, and I'm done. So we just need to execute that. So we'll start with this free body first. This was the free body diagram from A to B, and this was the free body diagram from B to C. Everybody see that? That's really the core of the problem. Once you do the actual conjugate beam here, for me that's about a third to half the work. Then after that, this is just a statics problem. So let's start with the free body diagram from A to B. So I'll draw that in a little more detail. So I've got the, what's the concentrated equivalent for this? It'll be acting down, and it'll be the load, which is 12 over EI times 3, so it's 36, right? So it's 36, and that will be kilonewton meters squared over EI. Because the height of the thing here is 12 kilonewton meters, and then you multiply it by 3 feet, or 3 meters, I'm sorry. And then I have what I'm looking for, the positive shear at B, and of course this is the positive shear at A. So if I sum moments about A, I should find the shear at B. So what kind of moment does this 36 kilonewton meters squared EI force have about A? Negative. So I got negative 36 kilonewton meters squared over EI. That's the force. What's the moment arm from A to the centroid? 1.5. And then I have the shear at B, which is also negative, and it has a moment arm of 3. So what is the shear at B? Looks like it's going to be 18? Yeah. Negative 18. So I got negative 18 kilonewton meters squared over EI. Does it make sense that at B you'll have negative slope? Well, how do you think this structure is going to displace? It's probably going to...
like a semicircle arch?
Yeah, oh, my pen just died. Let's get another one. Yeah, it's going to look like this. So you can see here at B that it does have a negative slope. So that seems reasonable. So what do we expect the displacement at C to be? Also, we should expect a negative slope. Let's see if that happens. Did this problem give you values for E and A? No. So that's it. It'll just be negative 18 kilonewton meters squared divided by EA. Is that the answer in the back of the book?
That's the slope, yes.
Okay. So now we can now transfer that on to the free body diagram from B to C. So give me a second to draw that out a little better. I forgot to write 3 meters on here. So this section will also be 3 meters. Now I'll have, I assume the shear was down here at B and then up here. So I'll continue that. So this is the shear at B if I assume positive. Of course, I got a negative answer, so when I plug it in, I'll plug in the negative value, right? Over at the fixed connection, I have the shear at C, which we're not interested in right now, but I do have the positive moment at C, which I am interested in. And then I have the concentrated equivalent of this force, which is acting down. So the area of the curve will be, it's a rectangle, triangle, so it's 1/2 base, which is 3 times height, which is 36, which is 12. And take half of that, so this should be what? 18, right? 18 kilonewton meters squared over EI. Now I'm going to be summing moments at C, so the distance will be 2 meters. You have a question, Mr. Simpson?
If we had taken, since we can with this particular load, if we had just done another shear moment diagram for conjugate B and just said the shear of conjugate B equals slope and then the moments at conjugate C equals the displacement, would that answer the problem?
Isn't that what we're doing?
Yes. I default to like shear moment diagrams and then just
but you're drawing, you drew the shear moment you drew a shear moment diagram for this problem.
Conjugate B.
Yeah.
Okay. That's my default. So
Well, that would work.
Okay. I just wanted to make sure.
You could do that. Actually, you end up having to do more work than what we're doing here, though, because you have to find both reactions plus the shears. To do it, you have to still do this, to find the reactions, and then draw your shear moment diagram. So here we only have to find one reaction. So your default costs you twice as much work. But the more important thing is, did you do it right? And can you do it in 15 minutes on the test? Probably. That's what you should ask yourself. Because when I'm done with this right now, all I have to do is... oops, I did it wrong. I'll do it this way. I'll sum the moments at C. So I have the moment at C, which is positive. This 18 kilonewton meter squared force is also positive. So 18 kilonewton meters squared, and that will be divided by EI in the problem. And it has a moment arm from C of 2 meters. And then this force, the way I've drawn it, is negative moment, right? So I'd say minus the shear at B times 3 meters. Now at this point, I could stick in my shear at B, which makes it a positive value. So when I solve for my moment, let's see, what do I get? So I'll get 18 times 3 is 54 minus 36. Do I get 18 again?
Yeah.
Is that right?
Yeah.
Except this becomes negative, so you add them together. Yes, so it's 54 plus 36, which is 60? I'm guessing.
90.
That's close enough. I had the 6 upside down. And that would be negative, right? So you should get negative 90 kilonewton meters cubed over EI. So this is a very long answer to your question, Mr. Kepler. Did you get negative 90?
I didn't get that, but I got confused because it's weird to me that on the first one, that when you found the shear, it's negative 18, so that means it's pointing up.
I try not to go back and change my directions. I just leave my number, whatever it comes out to be, and keep my original assumption for positive shear the same. And then when I actually need the value for shear, I just plug what it is. Just plug it in, let the signs take care of themselves. That's the sort of thing that will make your head spin on the exam if you're not careful.
So we're thinking.
So like in Mr. Simpson's way, that's my lockdown, that's my fail-safe mode. I just don't change anything. I leave it alone and just plug in the values that I compute. But when it comes to it, as Mr. Simpson so eloquently put it, if you can solve the problem and do it a different way, that's fine. Solve the problem. Ultimately, you're only going to be evaluated on whether you got it right or you got it wrong, and then where you made your error. So, okay.
Thank you.
You're welcome.